All right, gang, you ready for video number 3 in our thermodynamics journey? All right, so we looked at absolute entropy last time, introduced that concept. Let's take what we learned and look at entropy changes, which is ultimately, remember, ultimately we're looking at spontaneity, which includes enthalpy change, which we've covered before last semester. This semester will be entropy change, and then the little temperature that goes in there. The temperature we're not going to look at specifically, that comes into the equation. So really it's the changes in entropy, the changes in enthalpy, and how they dance with each other, right? Sometimes they're together, sometimes they're not dancing together. It gets more fun that way. Let's look at entropy changes qualitatively first based on what we did last video, and then we'll look at it quantitatively, which can get a little weird. I'll try to simplify it, take the calculus out, all that kind of fun stuff. All right. I'm going to look at 4, depending on the book you read and the stuff, these can be broken up into 6, 7 different categories, 3 categories, all depends. But just looking at quantitatively, let's look at how does entropy change if we change the temperature? Do we increase the temperature, decrease the temperature? We've kind of nudged you in that direction already. Phase changes, that should be pretty easy. Formation of a solution, which we sort of could put under number 2, but let's treat that separate. And then let's look at chemical reactions, right? And whether we form more gases or lose gas in the process. That's going to dramatically change the entropy during that chemical reaction. So we can actually predict qualitatively whether a chemical reaction will have an entropy increase or entropy decrease based on gases forming or being lost, going from reactants to products. So let's take each one in turn, do an example or two. Should be pretty straightforward. Let's look at temperature changes first. I think we already talked about this, but let's look at it more specifically. For example, let's take any species. Let's just take solid iron at 25 degrees Celsius and convert it, heat it up to solid iron at 75 degrees Celsius. We can qualitatively look at it and go, well, this probably has more entropy, right? But let's explain why. So this has a higher entropy, and this has a lower entropy, right? Because when you increase the temperature, it's twofold. You're increasing the number of available microstates because the particles have more energy now, right? Which means they can jump up to higher energy states. There's more energy states allowed, and the particles have more energy, right? So we've got a chance of increasing the different ways that they're arranged among those particular energy states, and the number of different arrangements are the number of microstates. That's that W term in the Boltzmann equation, right? So we could calculate that if we had the numbers of microstates. But just in general, and we're looking at the change, right? So remember, a change is the final minus the initial, right? So that'll be the final state minus the initial state. So if the final state is higher entropy than the lower state, then this will be a positive value, right? So this will be greater than 0. So delta S is positive. So we could predict iron at 75 degrees Celsius, converting it from 25 degrees Celsius to 75 degrees Celsius. Now note, we're not phase changing it. We haven't hit the melting point. That would be a whole different ballgame right there. But if we haven't caused a phase change, all we're doing is increase. So here's iron at 25 degrees Celsius. Those iron atoms are vibrating. Now it's 75 degrees Celsius. Ooh, they're vibrating faster, extending over more range. That's another thing we looked at last semester. That's why you get thermal expansion, because when you're at a colder temperature, they're vibrating like this. At a higher temperature, they're vibrating like this. So on a molecular level, you're increasing the volume of that, right? That's thermal expansion. That's why the density drops. When you have a substance at a higher temperature, its density is lower because you're dividing by the mass by a larger volume. Oh, my goodness. Remember that? So pretty straightforward. Increased number of microstates. Off we go. Let's look at the next one. All right, let's look at some phase changes. I think this is intuitively obvious because we know the entropy of a gas is way greater than the entropy of a liquid, which is greater than that of a solid. So you just have to look at what phase you're starting with to what phase you're going to. So for example, if you're forming a gas, doesn't matter what it is. Are you starting as a solid or liquid? If you're forming a gas, huge entropy increase. So the final entropy is greater than the initial. and they're going to have a very large positive entropy change, or delta S value. So that would involve evaporation, right? Liquid to a gas, and sublimation, solid to a gas, because you're taking like a solid with only vibrational states, and poof, now it's got translational, rotational, vibrational. It's all over the place. Same with the liquid. You're taking these constrained particles, with some rotations, and poof, now they're free to move everywhere. Totally huge increase in the number of available microstates. And likewise, but not quite as dramatic, a solid going to anything non-solid, that's going to have an entropy increase, right? So we already covered the solid to gas, right? So we'll put solid to liquid, right? Liquid formation from solids. So melting, you're taking a highly, highly constrained vibrational only solid and creating a less constrained, vibration, a little bit of rotation, a little bit of, translational motion liquid, an increase in microstates, not quite forming a solid, forming a gas, but that's going to be a positive delta S. Now, if you reverse this, if I go from a gas to a non-gas, right? So if I take deposition, gas to solid, or condensation, gas to liquid, that's going to have a negative delta S value, all right? Because you're going from a higher entropy to a lower entropy, and so when you subtract the lower from the higher, the final minus the initial, you get a negative value. And if we knew those values, right, if we knew the absolute entropies, we could do that. That's coming later. And vice versa, if we flip this, if we form a solid, right, either from a gas or a liquid, that's a large decrease in entropy. So that's going to have a negative value if we reverse these processes. Now, some people will put solution formation here as well, taking a solid solute and forming a solution. They'll put that under the phase change. We're going to do that separately just so we can look at that. All right, let's have at it. All right, let's have a look at solution formation. Got my ugly Pictionary skills going on here. This thing about going from home, I'm doing these live ones, so I just got this board, so I try to draw as best I can, but you get the point. All right. If you're taking a highly ordered solute, and we're specifically focusing on solids, I guess we could do liquids as well, but not gas. This does not work for gases. I'm going to put not gas solutes. All right? A little more complicated when you take a gas phase solute and dissolve that in a solvent. So let's focus on solids for now. If we take a highly ordered solid right here, right, say we got some alternating cations and anions, dissolve it in a less ordered solvent, right, because it's a liquid, it's got more microstates, and mix those together. Obviously, if that was water, for example, that water surrounds each of those ions. The partially negative oxygen would be attracted to the cations. The partially positive hydrogens would be attracted to the anions and form those little spheres around it. But hopefully you can just see the more highly disordered state here. Large increase in entropy in there. Not quite as much as you would think. It's a little more complicated because the water molecules kind of, you've got the ion dipole attractions there, so the water molecules organize a little bit more than you would anticipate. So you would expect you would expect just a pure delta S value without thinking about the attractions between the water and the ions. But if you take those into account, it may not be as big of an entropy as you would expect. That's not here or there at this point. We just know if we're forming a solution, entropy goes up. All right. Now, we're going to assume the same if we have two liquids, right? So we have a liquid solute, liquid solvent. They'll mix together and intermix. You have more available microstates going on there, right? But gas solutes, remember, gases are your primary huge entropy. So if you take a gas with a huge entropy and stick it into a solution, yeah, you're intermixing the particles, but you don't have that gas. You've lost your translational motion. So that's a tough one. So I'm not going to give you those kinds of ones. So we're taking solution formation from solid or liquid solutes. Increase in entropy. Let's do our last one. All right. This one, there's a lot of overlap between these. If we have a chemical reaction this time, the first thing you want to focus on is, are the number of moles of gas changing? So you look at the total number of moles of gas phase. It doesn't matter if it's a solid or liquid. It matters if it's a gas. Look at the total number of gas phase species on the reactant side, on the left-hand side of the arrow. Compare that to the total number of gas phase species on the product side, on the right side of the arrow. And you can just simply subtract them if you want to. But in general, if you're increasing the total number of moles of gas, that's a massive increase in translational states and allowable microstates. So that's going to be a positive delta S. Vice versa, if you're decreasing the number of moles of gas, say you go from 5 moles of gas total to 2 moles of gas total, that's a huge decrease in allowable translational states. So that's a more highly ordered situation, and delta S is negative. So if delta N gas, if the change in the number of moles of gas is positive, then delta S would be positive, right? Increase the number of moles of gas, you increase the entropy. If you decrease the number of moles of gas, you decrease the entropy. So let's show you real quick how to kind of eyeball it. You don't have to show calculations, you can just do it in your head. But let's say we got a typical chemical reaction. We got some 2 moles of potassium chloride solid, right? So I've been harping on you guys for a year on putting your states, guys. Don't get lazy. Put your states, because that matters in thermodynamics. Let's say that forms 2 moles of potassium chloride solid and 3 moles of diatomic oxygen gas. You're looking at the things with a G after it. Can you see on the product side there are 3 moles of gas? On the reactant side there's none. So let's do delta N gas. Right? That will be the moles of gas on the product side. Right? So this will be 3 moles minus the number of moles on the reactant side, which is 0, which is positive 3 moles. So we're going from 0 moles of gas to 3 moles of gas. You just take your final, remember a delta is the final minus initial. So you could go final moles minus initial moles, or moles on the product side minus moles on the reactant side. Boom, that's positive 3. So that's a positive delta S. So I would expect for this chemical reaction the entropy to massively increase, because you're going from no gases to lots of gas, huge number of increased translational microstates available for you. Okay? All right, let's take a look at some entropy changes quantitatively. This might take a couple of videos. All right, seems like a simple equation. If we want to calculate delta S, the change in entropy of some process, I'm not going to derive this for you, but it comes down to the heat and the temperature. These are the 2 variables that impact entropy. I think heat makes sense, right? More energy, more available microstates, right? You've got more energy for those particles to accommodate more possible microstates, so those should be directly proportional. Now, temperature seems intuitively weird to put in the bottom to me. It seems like it should be over here. So it's a little more challenging to think of it this way. You may need to read through a page and a half in the textbook for this to really hit home. But if you take a look at when you increase the heat, increasing the energy and the number of available microstates, it really depends where you're starting with your temperature. Right? So when you're starting at lower temperatures and you increase the heat, there's a proportionally larger number of available microstates available versus if you're starting at a higher temperature. All right. So proportionally, when you're changing the heat, it's more impactful at lower temperatures starting out with than at higher temperatures. So the lower temperature, if you divide by the lower value, gives you the bigger increase in entropy. So it's a proportional thing. Lower temperatures being more sensitive, I guess you could say, just more impacted with increasing number of available microstates. It's kind of weird to think about that way, but it's Q over T. Now, there's some constraints on this because enthalpy, internal energy, and entropy are path independent functions, right? You got state 1, state 2, those never change based on the parameters you set, so the difference should be set regardless of the pathway. But heat is path dependent, heat and work, if you go back to thermochemistry from last semester. So there's going to be some restraints on the heat flow here. This needs to be what's called reversible. So when we're going from state 1 to state 2, we just can't go, boom, I'm there. This doesn't work that way. So it has to be done in these infinitesimally small steps where you go, I want to get from here to here. So I do these infinitesimal, you can see where calculus comes from in the textbook, these infinitesimal steps where I do such a small change that it's reversible. I could go back to the original one and all of the things would be the same. So if I take a series of infinitesimal steps to get there, I get a reversible heat flow. Yeah, good luck doing that. So incredibly constrained. So we've got the reversible heat flow. So I'm going to put that here. I'm not going to go into gory detail on that. You can read about it if you want to. And we got the temperature. It's got to be in Kelvin. So you can see the units on entropy. It's going to be joules or kilojoules per Kelvin. Typically, we'll do that in joules per Kelvin. All right, you can see how that pans out. But again, this is very restrictive to use because of the restraints on the heat flow being reversible. All right, so we'll do one example with this where, there's a few situations in our macroscopic world in the laboratory where the energy change approximates a reversible heat flow. So let's go ahead and do that and do one problem, and then we'll kill this particular video and then get into some more gory details. This will get progressively crazier as we go. All right. So about the only way we can really use that equation to calculate entropy changes, it's quite restrictive because the reversibility constraints on the heat, is for phase changes. In our laboratory, those phase changes are closely resembling reversible processes. Not quite, but about as close as we're going to get. So we can say that Q reversible is approximately like, say, the molar heat of vaporization from going from a liquid to a gas, or the molar heat of fusion of going from a solid to a liquid. So if you don't remember those terms, go review that video on heat from thermochemistry, or review some notes on that from last semester. And again, just as a reminder, remember the change in the enthalpy. A lot of people call it heat, but technically capital H is enthalpy, a thermodynamic parameter. That is the heat flow at constant pressure. So whenever you see Q, a lot of times when we write Q, there's an assumption it's a sub P because we're almost always dealing at constant pressure in a laboratory, open to the atmosphere, right? So when you have constant pressure, the enthalpy change is the heat flow at constant pressure, which I think is delta U plus P delta V or something like that, right? So anyway, so let's say we have some generic liquid going to some generic gas. If I wanted to calculate delta S, this is a phase change, so we can approximate Q reversible. So delta S is Q reversible over the Kelvin temperature, right? Well, since this is a phase change, we can approximate that as the enthalpy change of that phase change, and this happens to be liquid to a gas or vaporization. So that would be the molar heat of vaporization over the temperature. All right, so all I have to do is find that molar heat of vaporization for that liquid, divide it by the temperature in Kelvin, and I've got the entropy change for that process. And if it happens to be occurring, if that's happening at the boiling point, I can just put the boiling point there. So I'm going to put up kind of a rough rule of thumb because most liquids, most of the time it doesn't matter the identity. You're just taking a certain number of liquid particles going to a certain number of gas phase particles. So the entropy change tends to be similar for many liquids unless they have some extreme intermolecular forces. So that leads us to kind of a rough rule of thumb we'll put on the next board. All right, so this general rule of thumb is that most liquids, right, that vaporize at their boiling point, which is, and think of the norm, we're going to say at 1 atmosphere, which is roughly 1 bar pressure. That would be the normal boiling point, right? If you're at a different pressure, that wouldn't be the normal boiling point. It'd just be the boiling point. For most liquids, the entropy change of the vaporization process at the boiling point is about 87 joules per mole Kelvin. So there's your units for the entropy. Remember, it's the Q reversible over the T. We usually do it per mole. That's not necessarily true for liquids that can undergo hydrogen bonding, right? So if you've got the OH, FH, or NH bond somewhere in there, it has just excessively higher intermolecular forces than you would imagine for a species, a molecule of that size. So that kind of holds them together a little bit harder than you'd think, right? A little bit tougher to disrupt those and put them into the gas phase. So that doesn't follow that general rule. So if you take a whole bunch of, say, nonpolar liquids, other liquids that can't hydrogen bond, calculate or measure their entropy changes for the vaporization process, yeah, they kind of average around 87. So if you're just kind of in a quick hurry and we'll do a question like this where we're calculating the entropy change for a phase change that involves going from the liquid to the gas. A lot of times, well, you don't need to calculate it. You can just stick in 87, right? Or maybe you're calculating the boiling point. What's the rough boiling point of a substance? It's a rough normal boiling point, by the way. We can stick in a value of 87 for that. And we'll do a calculation on the next board, and I'll show you how to quantitatively do that. But, we deal with phase changes enough in lab where this is a good little rough approximation to it. Right? Now, I've seen many different pronunciations. Troughton's rule, Troughton's rule. Looks like crouton to me, so I call it Crouton's rule. Troughton's rule. Or is it Troughton? I see trout. I don't care how you pronounce it, but I like croutons on my I miss my all-you-can-eat salad bars. You guys know I do most of your grading at all-you-can-eat salad bars. So, and I love croutons, so I'm going to call that Troughton's rule because it sounds like crouton. So, hey, if you disagree, that's fine. Text me. All right, let's do a mathematical problem for this, and we'll end this video. All right, I'm ready to put this to the test. So I'm going to show you two ways I can approach this on a quiz or an exam, and then we can calculate it on the next board. So I just wanted to explain how it can hit you with a curveball or a fastball first, and this will happen in your homeworks as well. Let's close that for the neighbors. All right, let's estimate, the keyword estimate there versus determine or calculate. Those mean two different things. So estimate the normal boiling point for benzene. Now, if I just say boiling point, the assumption will be the normal boiling point. Right? If I wanted something other than the normal boiling point, I would say that. So that's redundant. For benzene, if the molar heat of vaporization is 30.9 kilojoules per mole. Now, before we start this problem, I don't need to give you the molar heat of vaporization. I could have you solve for that using principles from last semester. So that's why I want to talk about here, and then we'll solve the problem. So if I say calculate or determine, that means I want a little more accurate value of delta S, okay? But for here, estimate means we could use that Troughton's rule, that 87 joules per mole Kelvin. So here's the process. We got our liquid. It happens to be benzene, but it could be any liquid, doesn't matter. And we're going to vaporize it, or boil it, in this case, to benzene in the gas phase. And it doesn't matter what the liquid is, but if this was a polar liquid, we probably couldn't use Troughton's rule, the 87 joules per mole Kelvin. But since this is a nonpolar one with no hydrogen bonding or anything, we're probably safe to estimate it using Troughton's rule. So we know our delta S. Note, if not provided the molar heat of vaporization, you can calculate it, right, using standard heats of formation that are listed in Appendix D in the back of your book, or if you're in my class, I typed all of those values up and posted it up on my website, all right, and you can print that out. So you can use this equation. Remember, blow the dust out of your brain. Go back and review thermochemistry. You can calculate the energy for the heat of a reaction, or the enthalpy change. That's that little zero, that little not symbol means at standard conditions. It's just the sum of the stoichiometric coefficient times the molar heat of formation, standard heat of formation of your products, minus the sum of the coefficient from the equation times the standard heat of formation. So you look at these standard heats of formations for your product and reactant species in Appendix D or on my handout, and then the stoichiometric coefficients come from the equation. So these would both be 1. So in this case, I'd take 1 times the standard heat of formation for benzene in the gas phase, minus 1 times the standard heat of formation for benzene in the liquid phase, products minus reactants. And if you had multiple products, you just add those together, multiple reactants, add those together. So that's all review. So you can calculate that if you're not provided that. So I just wanted to specify that one thing there. So let's go ahead and do the calculation. Since we can estimate it, we're going to use Troughton's rule, and it's a nonpolar liquid. It doesn't hydrogen bond. If it hydrogen bonds, you'd have to calculate delta S. I'm going to show you how to calculate delta S this way. We can do it exactly the same way. So if I ask you to calculate it, a more specific value, or it hydrogen bonds, you won't be able to use Troughton's rule and use that 87 joules per mole Kelvin for the delta S vaporization. You'll have to calculate it this way. You just put an S value there. So let's do these numbers. See if you can calculate it real quick. So pause the video, calculate it, see if you get what I get. Did you get it? Did you get it? Did you get it? Did you get it? All right. So here, and you don't have to write all this junk on an exam or test. But because benzene is nonpolar, it doesn't have hydrogen bonding, and we're estimating the boiling point. That's the green light. That's the red flag to go, oh, I can use Truton's rule that the molar entropy of vaporization is 87, approximately. So that's going to limit us to 2 sig figs there, right now. So we know, where'd my black pen go? We know that the change in entropy of this process, right, is equal to Q reversible over the temperature, and this will be the boiling point, the normal boiling point, which will be approximately delta H vaporization over the boiling point. Right? So we'll just take a little b. You don't have to put the sub b there for the boiling point. And since we are going to estimate that using Truton's rule, and I gave you the molar heat of vaporization, we can solve for the boiling point. It's pretty simple. Once you've identified your values, it's a pretty simple process. And again, if I don't give you delta H vaporization, use that equation in Appendix D with the standard heats of formation. And if we can't use Truton's rule, we're going to have to calculate delta S using Appendix D as well, using standard heats of formation. So we can do that. And I'll introduce that in the next video. Let's calculate this puppy. All right, so I'm solving for the boiling point. So I like you to isolate your variable. It's nicer for the reader. Don't make the readers do the algebra. So the boiling point, the normal boiling point, let's move that over, will be the molar heat of vaporization. We're going to swap places with the boiling point and the delta S. All right, so isolate your variable for me. So I gave you the molar heat of vaporization is 30, what was it, 30.9, I think? 30.9 kilojoules per mole. I think that was 30.9 kilojoules per mole. Let's divide by the entropy. Now, when you divide something using dimensional analysis, you just multiply by the inverse. So what I'm going to do is I'm going to take the 87 joules per mole Kelvin. So instead of dividing by it and having a numerator denominator in the numerator and a numerator and denominator in the denominator, red leather, yellow leather, toy boat, that's a tongue twister there. Try doing that. Red leather, yellow leather, red leather, yellow leather, red leather, yellow leather, red leather, yellow leather. Good luck with that. So I just inverse. I'm just multiplying by the inverse. Okay. Can you see how the moles cancels out? Bye-bye. Hey, wait a minute. Show your work always, because kilojoules don't cancel out joules, and I'm trying to get the temperature right. Now, I didn't specify degrees Celsius or Kelvin, so I'll just leave it in Kelvin, but you could convert that to Celsius. So let's convert our joules. So we got 1,000 joules per kilojoule. You're going to see this happen all the time when we're using enthalpy changes and entropy changes. Entropy changes are always joules per Kelvin or joules per mole Kelvin, and enthalpy is always kilojoules per mole. So you're almost always going to have that 1,000 to 1 conversion so we can cancel out. And that's going to just leave us with Kelvin. So we've got 2 significant figures because we're estimating with Truton's rule. 3 there, that's exact. So our answer is going to be good to 2 significant figures. So if you pop this out, I get 355.1. Good to 2 significant figures. So that's a little bit closer to 360 Kelvin than it is to 350 Kelvin, because 355.1, it's a little bit. So that's going to go to 360 Kelvin. All right? And if you want to convert that to degrees Celsius, which is typically more how we think, just subtract your 273.15. And then you would get your answer in degrees Celsius. So watch out on an exam or quiz. If it asks for the temperature, does it ask for a specific unit, degrees Celsius, Kelvin, or degrees Fahrenheit? If it doesn't, just leave it in what you have. Don't waste your time converting it to another one. But if you subtract 273.15 from the non-rounded value, you get your answer in degrees Celsius. That's how we're going to use it. We'll do some crazier stuff in the next video. Rock on. Go get some food.